With gases and stoichiometry, we can also do comparing volumes. The reason it has to be in a gaseous state of matter is that with gases, the actual mass or size of the molecule has a very small influence on the amount or number of atoms that you have in that sample. So there's a scientist whose name is Avogadro. He's the guy who gives us Avogadro's number, which is again 6.02 times 10 to the 23rd. But Avogadro also did a lot of research on the relationship between moles and volume of gases. So he found that as you increase the number of moles of any gas, there's a direct relationship to the increase of volume. So it's really independent on what that gas is, whether it's O2 gas, N2 gas, carbon dioxide gas, whether it's an atom gas composition or if it's a molecular gaseous composition. So with gases, liquids, it's different, but gases, the volume has a direct relationship to the number of moles. Because of this, if we say that we have 2 liters of N2 added to a bunch of O2, we want to know how many liters of NO2 are produced. We can use that molar relationship because moles and volume have a direct relationship as well. So we talked about molar ratios. From molar ratios for gases, we can also get volume ratios, basically. So if we have 2 liters of N2, based on our balanced chemical equation, we will get 2 liters of NO2 for every 1 liter of N2. Because the balanced chemical equation, we have a 1 coefficient for N2 and a 2 coefficient for NO2. So that would tell us that we would get 4 liters of NO2 gas. We can also relate this volume to moles, okay? So again, Avogadro did a lot of research related to gases and moles. And basically what he found was that at standard temperature and pressure, he could find out how much liters volume of gas there are with 1 mole, per 1 mole, okay? So standard temperature and pressure means that we have 0 degrees Celsius and 1 atmosphere pressure, okay? If you change the pressure or you change the temperature, then this relationship that we get is also going to change because gases are heavily influenced by temperature and pressure, which we will talk about later. So again, based on Avogadro's hypothesis, at certain temperature and pressure, all volumes of gas, no matter what that gas is, contains the same number of moles. And he found out that 1 mole of any gas takes up 22.4 liters at standard temperature and pressure. Again, if there's a different temperature pressure, then that is going to change. So again, using this equation, if we have 2 liters of N2, again, added to excess oxygen at standard temperature and pressure, which I did not include in that question, how many moles of NO2 are produced? So again, we start with our 2 liters of N2. We use our volume ratio, saying that 2 liters of NO2 will be produced for every 1 liter of N2 that's used. And then we can find the number of moles by saying 1 mole of NO2 is going to be in or be contained by 22.4 liters. So here my liters of N2 cancel out to give liters of NO2. My liters of NO2 cancel out to give moles of NO2, which is what I'm interested in. So I take 2 times 2 divided by 22.4, and I get 0.18 moles of NO2 produced. If one of these were liquid or solid, we couldn't be using this mole volume relationship. We can also determine the mass, okay? So same problem, standard temperature and pressure, this time how many grams of NO2 are produced. And we just have one other step. So remember, to go from moles to mass, we're going to be multiplying by the molar mass of that substance. So we take our known 2 liters times 2 divided by 1 times 1 divided by 22.4, and then multiply by 46.01 divided by 1, and we get 8.3 grams of NO2. This 46.01 is the sum of the molar mass of 1 nitrogen plus the molar mass of 2 oxygen. So that's where that number came from. This is again the relationship between moles and volumes of gas at certain temperature and pressure. And this is our volume ratio that comes from the balanced chemical equation. So with this, I will post this on Classroom, but if you were in my chemistry class, I did give like a little roadmap that kind of gives you an idea of how to go from one unit to another. So whether you're given grams and you want to know moles, or moles and you want to know number of atoms, molecules, volume. So this is kind of my dimensional analysis little roadmap is what I call it, that you can kind of use to review. So I can scan that and put that on Classroom. It has pretty much all the conversion factors that you need, including when you're using Avogadro's number and when you're using molar mass. Okay, so again, let me know if you have any questions. That is stoichiometry in a nutshell.